Okay, hi everybody. Thanks for coming to this week's seminar. If you're watching on YouTube, please feel free to put any questions you might have in the chat and we'll try and ask them at the end. And I'll now pass over to Janine, who's going to be introducing our speaker today.
Thanks very much, Caitlin. So I'm delighted to introduce Johan Lissenberg. He's a reader at Cardiff University. He did his undergraduate studies in Holland, where he was born, and he obtained his PhD from the University of Ottawa in Canada. And that was where he worked on the suture zone of the Iaptus Ocean in Newfoundland. He went on to do postdoctoral work at Woods Hole Oceanic Institution and IPGP in Paris, looking at oceanic magmatic systems. So, and I asked Johan to tell us something fun about himself when I was asking about his bio. And he told me that he sailed on the IODP expedition that managed to recover only 1 meter of core. So that was a very expensive meter of core.
Yeah, that's right. Yeah.
So I'm very happy to introduce you, Johan.
Okay, thanks. So what I'd like to do today is to talk about magma reservoir evolution with a sort of perspective from the mid-ocean ridge system. Before I start, I want to just pay tribute to people that have contributed a lot to the work that I'm covering. A long-term collaborator at Cardiff, Chris MacLeod, but particularly my PhD students, Emma Bennett and Matthew Locke, as well as my postdocs, George Cooper, Alexandra Yang, and Sarah Lambert. So, you know, they've helped shape the kind of work that I'm talking about today. So the international sort of context of this is that we're sort of shifting the paradigm about magma reservoirs at the moment from magma chambers to mush reservoirs. So historically, magma reservoirs were viewed as the sort of classic magma chamber, so which is defined, at least by Wikipedia, if that's anything to go by, as a large underground pool of liquid rock. And you know, that idea has permeated academia for a long time, and still does to some extent. It's certainly also still the standard model in what we tend to teach our undergraduates, and certainly that is also the case in the popular media. So the magma chamber concept has been long-standing and quite a powerful one. But there's a shift at the moment towards mush reservoirs. So whereas in the classic magma chamber on the left-hand side, you would have convection, you would have a largely liquid body in which crystals settle to the base. They might crystallize on the wall and flow back down. You could stope some country rocks. And those are the kind of typical processes that igneous geologists have contemplated for at least a century, sort of since Bowen. The alternative, which is emerging, is rather that the magma reservoirs are crystal rich, which is essentially a mush, so crystals with interstitial melt. And interestingly, Bowen already sort of kind of hinted at the existence of both possibilities for differentiation, in that he was, you know, he is still, I guess, known most for fractional crystallization, which was very much on the magma chamber type side of processes. But he also said in 1915 that the sinking of crystals in the fractional crystallization paradigm would work, but also that you could squeeze out residual melt from crystal-rich environments. So that's much more sort of on the mush side of the sort of spectrum of systems. So this is essentially where the current debate is, you know, how magma-rich or crystal-rich are systems, and that's the kind of issue that I want to talk about today. So the drivers for the change from magma chambers to mush reservoirs are quite numerous. But the most obvious one, really, and that the one that probably dates back the furthest, is geophysical data. So here in the center panel at the top, you can see a seismic tomography image of the East Pacific Rise, so fast spreading mid-ocean ridge. The MOHO is here, so don't worry about anything that happens at the bottom of the diagram. The data are here, and that is essentially the velocity anomaly, the seismic velocity anomaly of the P waves. And they obviously define this magma reservoir here, which has a negative velocity anomaly. Then when you invert that for melt content, you find that melt contents are as, up to sort of 38%, but as low as just a few percent, depending on the assumptions you make about what kind of geometry the melt has within the crystal framework, whether it's in spheres, whether it's in films. So there are some assumptions here, but whichever one you choose, you end up with a crystal-rich system overall, and not at all a melt-rich one. And so this dates back to around the 1990s, so that was quite some time ago. And I think certainly in the mid-ocean ridge community, that change from melt to mush was accepted on this basis fairly early on. Certainly from a geophysical perspective, I think petrologists have struggled a lot more to adapt to that sort of geophysical reality, but I think we're certainly moving in that direction at the moment. So geophysical data have defined that much. There's also petrological data. This panel here on the right is for Mount St. Helens, and it contains a number of interesting observations. First is that the cores of plagioclase crystals that have erupted in the 1981 eruption are relatively evolved. They've got low anorthite content, which means they formed at reasonably low temperature, whereas the rims formed at higher temperatures, which suggested that actually before eruption, which grew those higher temperature rims, actually the system was fairly cool. And actually, age dating of those crystals suggests they've been sitting there for thousands of years before eruption in a fairly cool state. Zircon provides an even more interesting perspective. It's a lower temperature phase still. It's only probably grows at temperatures of 700–800 degrees or so. And yet it is present as crystals in these eruptions for a few 100,000 years, which suggests that the system had remained cool for a long time before eruption, but managed to rejuvenate upon essentially just before eruption. So that suggests the overall dominant state of the reservoir was rather cool and crystal rich just before eruption. And the final driver is, if you do thermal models of magma reservoirs, then it turns out it's actually rather difficult to maintain a large liquid magma chamber. You need to keep on replenishing it to provide enough heat to keep it liquid, which is difficult to do. So combined, that has sort of driven the paradigm shift towards crystal mushes. But it's not universally accepted, for one. There's still debate about just how mushy systems may or may not be. And there's certainly some high-profile papers appearing that still argue that the magma chamber remains a viable explanation for the observations we have. And in reality, which I try to capture here at the bottom, we have an array of different opportunities. It's interesting, the melt content of these four cartoons is actually very similar. So except with the exception of the classic magma chamber, but these other three alternatives have the same melt fraction, just in different distribution. You might have a system where you have fully solid crust, just with individual sills which operate in isolation, and so basically all the processes happen in isolated sills which then erupt. You could have a largest region of sort of low melt fraction mush, but with sills or other bodies within it, or you could have a pervasive mush with not many sort of higher melt fraction areas in it at all. And so, we're somewhere on this spectrum, and different systems might be on different parts of the spectrum. So really, the goal is to try to find out where on the spectrum we are, and what that means for our understanding of igneous processes. So why do we care about this? Well, I guess, the evolution of igneous rocks is one of the fundamental aspects of geology. They obviously formed much of the crust that we have. And at stake, really, are basic concepts like the origin of igneous rocks, the meaning of the word differentiation, and the formation of plutonic systems. So quite a fundamental problem, but also quite an applied one, in the sense that the different models have very different implications for, say, delivery of melt to volcanoes, and therefore of monitoring of volcano and the associated hazards. Similarly, many ore deposits are related to magmatic systems, and the kind of models we have for magma reservoirs, particularly for layered intrusions and their chrome, PGE, nickel deposits, are fundamentally dependent on our understanding of those reservoirs. And melt delivery and the thermal state of reservoirs, of course, also has fundamental implications for geothermal energy, which is dependent on the flux of heat, the timescales and magnitudes of those being delivered to the system. So overall, I think it's a compelling case that we need to try to understand these systems better. So the questions I want to address today are where, how, and at what kind of scale is melt delivered to the reservoir, how melt is then transported in it, through it, and out, I guess, and whether melt evolution, so differentiation, the differentiation process, whether that occurs in melt-rich or crystal-rich environments, because there are very different predictions as to how the system would behave between those two. So these, I'm going to essentially address these three questions in sequence. I'm going to start off with melt delivery and then move on to melt transport and melt evolution later. So I'm using oceanic systems as case studies for a number of reasons. The first one, which is that there is essentially no interaction with older crust, no issues with assimilation of old and or compositionally very different crust like you would have in continental systems. And that means we can really sort of isolate the intrinsic magmatic properties of the system, which is important. We can't be distracted by external forcing if we are trying to look at the intrinsic properties of the system itself. So that's where oceanic systems are very good. There's also a very, very well-defined geophysical framework for mid-ocean rich systems. And there's just an example here, which we'll come back to later. But this kind of highlights the higher resolution that oceanic seismic data have compared to continental ones. What you can see here on the left is the data. There's this really prominent anomaly here. This is in reflection data, which is the top of the magmatic system. And that anomaly has a negative amplitude, which means that you go from solid to liquid. And that liquid in the cartoon here is at the top, and it's called the AML, which is an axial melt lens. That's what it's called. At fast spreading ridges, it seems to be present along the entire ridge axis just about. It varies in crystal content. It's sometimes fully liquid. Other places it's more crystal rich, but it seems to be present just about everywhere underneath the ridge axis. So this melt lens, and then underneath that, actually, there are some smaller amplitude anomalies that maybe you can pick out if you're a geophysicist, which I'm not. But there are some melt lenses beneath the axial melt lens as well. So they are called subaxial melt lenses in the cartoon here, SAML. Anyway, so this system is only about 4 kilometers high, and yet we've got some fairly good constraints. On oceanic systems that we can achieve that sort of resolution is more difficult to achieve in the continents. And finally, we have places where we can sample the full stratigraphy of the reservoir and even its source. So we can sample mantle rocks, abyssal peridotite, a full section through the plutonic rocks, through the reservoir, and the overlying volcanic rocks as well. So we can trace processes and compositions all the way from source to surface, which is very powerful, and again, something that is difficult often to do in continental settings. So I'm going to be particularly talking about Hess Deep today. Hess Deep is a rift valley in the equatorial Pacific, as you can see here on the diagram on the left. It's right here at the triple junction between 3 plates. And what is happening is the Caucasus-Nazca Ridge here, which is east-west, is propagating into just over 1 million-year-old crust that formed at the East Pacific Rise, that formed at a fast-spreading system, and is now being rifted apart by this propagating rift. And you can see the close-up here on the cartoon on the top right, you can see the propagating Caucasus-Nazca Ridge rifting apart the East Pacific Rise crust. And this is a bathymetric graph here looking into the rift, where you can see the uplift of the section where we've been able to sample the full stratigraphy of a fast-spreading system. So there have been a number of expeditions to this place. It is probably the only place we know of where we have a full transact from mantle to the surface in fast-spreading crust. The first one was ODP drilling, which drilled right at the top of this big fault block, which is in the middle of the Rift Valley, and that sampled gabbroic rocks. There was an expedition that I was part of that was NERC funded, where we used a remotely operated vehicle here, this ROV hanging off of the side of James Cook, where we were able to sample all the way up and down the fault block here in excess, basically mantle rocks at the very depth, and then all the way through the plutonic rocks. And then IODP went back a few years ago and drilled some of the gabbroic rocks here at the deeper part of the section. So overall, what you see here is these yellow samples are all Cocos Nazca basalt. So those are basalts of the propagating rift tip. The fault block is the East Pacific rise crust, which goes from some mantle rocks at the base and primitive gabbroic rocks all the way through the plutonic section to the top of the plutonic reservoir right here, just past on the north side of the summit of the block. And then there are upper crustal rocks just here on the western side, as well as the rift wall on the northern side. And just a quick note on methodology. I'm using a lot of element maps in this talk. So essentially, rather than doing spot analyses of mineral compositions, modern EDS systems now have such high count rates, in excess of 1 million counts per second, that you can just element map your entire thin section at a very high resolution. And so you can get a full overview of all the compositions that you have in your sample. And it sometimes reveals really surprising things. You know, this thin section in plain light doesn't really show anything very much. It's just an olivine gabbro. But then the element map clearly shows that there are very strong compositional gradients in the sample, which you might have not picked up otherwise. Certainly petrographically, they are not easily distinguished. Anyway, so we now routinely map these compositions on the thin section scale, and we then quantify the element map. So this element map here on the right is qualitative. It's just sodium in blue, iron in red, and magnesium in green. So it's a qualitative distribution of different elements. But we can then essentially invert those data for quantitative mineral composition. So in this case, the same sample, the plagioclase anorthite composition, magnesium number in pyroxene, and phosphorite content of olivine. And so that then enables you to do sort of compositional analysis, population statistics on the distribution of mineral compositions in a sample. So here's a different sample. Another example of full thin section scale. This is plagioclase anorthite content, which obviously is quite variable. You can then just make a histogram of that, so you can look at the different populations you have in there. And then what I'm going to do later in the talk is, this is great and a lot of detail on single samples, but if you want to compare samples, this is all quite tricky. So I'm going to compress the histogram into a 1D line, which essentially represents the histogram. So this peak is obviously the darkest color in the line diagram. The secondary peak is right here, and this tail is here in green to blue. So essentially, you can capture the histogram in a 1D line, and you can compare the lines up and down the section to see where mineral compositions are headed up and down the section. Okay, so back to Hess Deep, and actually let's get into the actual observations about the plutonic stratigraphy. What I was surprised by when we were on that the JC21 expedition is just how much the plutonic stratigraphy at Hess Deep resembles the Oman ophiolite, which is always been argued and widely accepted to be a fast-spreading analog on land. So perhaps not that surprising, I guess, but I had expected at least some differences that were obvious, but that turned out not to be the case. So at the bottom of the plutonic section in Oman, as well as Hess Deep, we have layered gabbros. This is just the whole rock stratigraphy for Hess Deep to give you a kind of context. So this bottom half of the section is where we found those layered gabbros, and those were drilled then by IODP a few years ago. And they clearly recovered core with nicely layered gabbros, which look quite similar to what you see in Oman in outcrop, as shown in this photograph. So if you move up section in Oman, you get these foliated gabbros, which are very distinct from the layered gabbros. They don't have any layering, and instead they have a very strong mineral fabric, which is paleovertical. I hope you can just about pick it up here in the field photograph. If not, you can clearly see it in the thin section. Quite a strong alignment, mostly of plagioclase in a paleovertical direction. And when ODP drilled at the top of the fault block that I showed earlier in Hess Deep, they found the same relationship, unlayered but vertically foliated gabbros there as well. So again, there's a good analogy between Oman and Hess Deep. And then at the very top, maybe the top 100, 200 meters or so, in both Hess Deep and in Oman, you see these very textured gabbros. So they have hugely variable textures, grain sizes, and mineral nodes on very small scales and sort of in irregular patches. No more fabrics in the rock. These are essentially isotropic from a structural perspective. So those are essentially the three stratigraphic units that make up the reservoir. So what I'm going to be doing is I've taken this cartoon and I've built our magma reservoir here, but it's entirely blank, and I'm going to try to fill it in with snippets of information as we go along. We've got the mantle here in gray at the base. It's delivering melt to our reservoir. The purple is already crystallized plutonic rock, so they are basically off-axis cooled versions of what happens in our magma reservoir. Then in green, we have sheeted dikes feeding pillow lavas at the top, and we're going to try to fill in the reservoir with information. Okay, so I already talked about the axial melt lens. We know from seismic reflection studies that it is present just about everywhere along axis on the East Pacific Rise. So I've drawn in the axial melt lens here, along with a few of those subaxial melt lenses that are evident on the seismic reflection as well. So that's the first bit of information we have, particularly the persistence of this melt lens at the top. So let's actually get into the science then, melt delivery. So here on the left is one of those sort of compilation of histograms, I guess, but in the form of 1D lines of the Hess Deep stratigraphy. So on the x-axis is the anorthite content of the plagioclase as compiled from the element maps of the thin sections. And on the y-axis is the stratigraphy. And I've just stacked the samples on top, sort of one line per sample, with the exception of ones where I say n equals, and then it's obviously the line is a combination of different samples. Obviously, I can't fit all of these in, and these are for individual IODP drill holes. So I've basically compressed each drill hole into a single histogram. And so we've got our units here. We've got the layered gabbros at the bottom, then foliated gabbros on top, and very textured gabbros at the top of the reservoir. So what you can see here is essentially the trend of differentiation that the reservoir is recording. So we've got anorthite contents around 80 and plus or minus a bit. Clearly the layered gabbros, different layers might have different compositions. So you see that variability here. But on average, we're in the sort of high 70s up to about 80 and a bit. This drill hole, IDP drill hole, was more primitive still. It's around 85 at its sort of modal peak, if you will. So fairly primitive compositions at the base, high anorthite contents. And then as you get into the foliated gabbros, you can clearly see a change towards more evolved compositions. And as you get to the very textured gabbros, you can find some samples that are more evolved again, others a bit less so, but certainly a lot more evolved than anything that is recorded in the layered gabbros. So we can try to translate those compositions to melt compositions using this model. This is a model that is made in melts, which compares the different degree of differentiation as recorded by the magnesium number of the melt versus the anorthite contents in crystals that would crystallize from it. So we can basically take our, say, 80 from the bottom here. Here's our anorthite 80. That translates to a melt composition of essentially a primitive mold. So primitive melt delivered to the crust would crystallize our layered gabbros. In contrast, if we look at some of the compositions here in the, say in the foliated gabbros, you're looking at maybe an orthite 60 or so. That would be here on the diagram. You move up and move sideways. You're looking at melts of about a magnesium number of 50 odd, which is really quite evolved, and in fact more evolved than typical mid-ocean ridge basalt. So what that suggests, the fact that we see primitive melt compositions recorded at the base and that more evolved melt composition at the top, is we seem to be having an upward differentiation trend throughout the reservoir as a whole, and the melt delivery, the primitive melts coming from the mantle, are only recorded in the bottom half of the section. So that suggests that there should be deep melt delivery to our reservoir. That's kind of akin to an existing model for fast-spreading ridges, which is called the sheeted sill model, where you've got a series of sills essentially differentiating upwards. There's an alternative model, though, which says, actually, no, forget about that. All of the primary melts from the mantle go straight to the melt lens at the top, the axial melt lens that we talked about, and those very textured gabbros, if that is the case, should record those. So my PhD student, Matthew Locke, did a really detailed study of the axial melt lens samples that we obtained to see what kind of compositions we recorded there. And this is the histogram we found. You've seen it before. This is the one I used as an example. There is a peak here that forms the framework of many of these plagioclase crystals at about an orthite, you know, in the sort of 65, peaking towards sort of 70-ish, which forms the framework. And that framework, if we go back to the same diagram, is in equilibrium with typical East Pacific rise more, which suggests the melt lens, the framework that forms upon the melt delivery, is formed from already differentiated mid-ocean ridge basalt, so not primary delivery. We see a lot more information here in the diagram. We see some very rare, they only form about 2.2% overall, a sort of resolved primitive cores, which might have been carried as anticrysts with the melt. And we see a lot of evolved rims, and then later even some interstitial material, which is essentially melt that was trapped after the crystallization of the framework and just crystallized progressively in situ. So I think this, the idea that primary melts or primitive melts get delivered to the melt lens, we can now conclusively rule out. We've looked at the full inventory of what's there in terms of crystal compositions, 34 thin sections fully quantified, and so there just is not a record of primary melt delivery at that level. So I think it's safe to say, therefore, that melt delivery is deep in the reservoir. So I've added a rather random shape, I guess, of delivery, but the idea, I think, predominantly is that it would be in more horizontal bodies rather than vertical ones, based on the fact that we see paleo-horizontal layering both in Oman as well as Hess Deep. So it's essentially most likely a type of sill complex. And we now then also can say that the axial melt lens at the top is fed by already differentiated mid-ocean ridge basalt, and that differentiation happens in a deep crustal complex. So how about melt transport? In the maps, we see a lot of evidence for porous flow. So porous flow is essentially flow of melt through the interstices of a crystal framework. And we can pick that up beautifully in the maps. You can see these more lighter blue areas here, which go through the sample, and they're connected to these darker red rims on the pyroxene, the bluish plagioclase. We see melt transport in these sort of networks forming rims on our crystals. You can see them in a pervasive way, like the one on the bottom left. You can see more focused ones, such as the ones on the right, where you can clearly see defined sort of channels of running through the samples. Key, though, is that this, from a textural perspective, precedes the occlusion of porosity. So the system, this isn't melt that is trapped after the crystal framework formed and then just crystallized in situ. The fact that it forms a connected network and channels suggests that this is a connected network of melt through which you can actually transport melt rather than just trap it. And that's consistent with field evidence we see, and this dates back all the way to my PhD. So this is in an ophiolite in Newfoundland, where you can see these very sort of almost wispy layers that are rich in pyroxene in an otherwise olivine and plagioclase rich rock. You can see them as sort of slightly more defined and sharper features as well. And these are essentially porous flow channels. Now, the critical thing about porous flow is not just a mechanism of transporting melt, it's actually reactive. So if you go back to the thin section and you look at these red rims on the pyroxene, you can see reactive features. You can see reactions of the initial pyroxene, which is gray in the photomicrograph on the top right. This is in cross-polarized light. And there's a second generation of CPX that sort of forms blebs within the original CPX, along with amphibole as well. So there's clearly some kind of reaction going on. And the ultimate evidence of that, I guess, is that you see symplectites of this developing. So this is a symplectite where CPX1 reacts to CPX2 plus amphibole in a symplectitic intergrowth. So we see reactions happening during this transport from a textural perspective. And so it's important to understand the sort of mechanisms and rates of that. And so my postdoc, Alexandra Yang did some experiments where we juxtaposed a troctolite with a basalt, heated it up to the liquidus temperature of the basalt just to see what would happen. And this ran for 6 hours, so fairly short experiments. I don't want to talk too much about the detail. The one thing I want to say is in the panel here on the right, is we started off with mental olivine, just typical San Carlos, Forsterite 91-ish clear olivines. And after the reaction, we noticed there are now plagioclase inclusions in the olivine, which requires that the olivine is dissolved and reprecipitated. It has undergone a reaction, not just of dissolution, not just of precipitation, but a dissolution reprecipitation reaction, through which it has now managed to include what was a matrix phase in plagioclase. So that's an important thing to keep in mind in terms of how these things happen, but also the rate of this was very fast, right? So we only ran this for 6 hours and we managed to essentially have these reactions go to completion along with any sort of compositional modifications that might yield. And that's only in 6 hours. Clearly, magma reservoirs have a lifespan that is a lot longer than that. So certainly the experiment suggests that a lot of reaction might happen in natural reservoirs. So I guess in terms of our magma reservoir model, we can start to envisage that there might be porous flow. I've just made them light gray here because we don't yet know, in the point of this talk, what kind of scale this might be operating on. Is it only a local scale where one sill, say, forms a crystal framework and then you have melt flow through the framework of that individual sill, but the country rock is maybe solid and so the porous flow doesn't extend very far? Or is there much larger scale flow? So at this point, we don't really know. We just see textural evidence that it happens and that it happens beyond just trap melt and that there is genuine melt transport through porous flow. However, much as though we see evidence for porous flow on the thin section scale, there must be rapid channelized sort of old-fashioned dike-like melt transport from the deep layered gabbros to the surface, essentially, because the basalts that erupt at the surface are in equilibrium from a crystal chemical perspective with the layered gabbros at the bottom, and not so much with the foliated gabbros or the very textured gabbros at the top. So the compositions of the basalt indicate that they are derived from the deep part of the section. And the only way in which you can have an efficient enough mechanism to feed those eruptions from the deep section is if they essentially dike their way through this part of the system, because we don't have a record of those compositions in this in the top part of the section at all. So they just shoot straight out to feed first, I guess, the melt lens and then straight out to eruption. So I guess the implication, which is backed up by diffusion studies, is that the residence time of morb in the melt lens is actually very short. So you dike your way out of the sill complex at the base. You bypass essentially much of what is happening in the foliated gabbros. You feed the melt lens, and as soon as you've replenished it, you go straight out to feed your eruptions. So the compositional stratigraphy essentially suggests that you need rapid channelized melt transport as well as porous flow. So we seem to have a combination of the two. And we also think that that might account for the actual observations of the foliated gabbros. Remember, they have these vertical mineral fabrics, and those fabrics are magmatic fabrics. They form during flow of crystals and melt together. They didn't form sort of subsolidus. There's no plastic deformation recorded in these crystals. So they were aligned while they were still in a magma. So what we speculate happens is, you take one of these sills, you destabilize it, it feeds an eruption through this focus channel, and essentially you align the crystal framework along the edges of that channel in a vertical way. And so you obviously go through this process many times, and that's one of the interesting things I find to think about a fast-spreading ridge reservoir in this way. If the reservoir is about 8 kilometers wide from geophysics, and we obviously know the spreading rate, we also know that more eruptions happen about every sort of 10 years or so along a fast-spreading ridge. So if you sort of do the back of the envelope, then any section of mush, essentially, over the reservoir will have been part of the reservoir for about 5,000 eruptions. And of course, we don't know quite how many times of whether that equals 5,000 times of replenishment, but certainly the idea that you align the wall of one, during one channelized event, by the time you've got 5,000 events going through, you might really well start to align the whole system. So that's where we speculate these vertical fabrics originate. So we can conclude, I guess, from the melt transport part of the talk that the low crust is essentially a dual porosity system. You've got high porosity melt transport and high porosity, I guess, sills, so melt-rich parts of the system, but that you also have melt transport by porous flow. So you've got melt transported by two different mechanisms on two very different timescales: slow porous flow versus fast channelized flow. So then finally, melt evolution. We know a lot about major elements in mid-ocean-rich basalts. We've got about 10,000 data points for it, which is rather a lot. And they've always been used to infer the degree of melting of the mantle, the extent of differentiation, and the depth distribution of magma reservoirs are essentially used as a geobarometer. And we know, this is a geochemically fairly simple system. This phase diagram has been in existence since the 50s, so we know very well how this system should behave in a fractional crystallization scenario. And this is magnesium versus calcium of this, in this case, the Atlantic data set, which is a very extensive data set. And if you start with any sort of primary melt here indicated by the star, you can either differentiate it at low pressure and you can go this trajectory, or you can do it at higher pressure and then clinopyroxene saturates earlier, so your calcium goes down early, and you take this trajectory. And together, sort of polybaric differentiation, I guess, would cover this whole trend. So the low pressure trends on this side, high pressure trend here, anything in between or any mixing between different melts that have differentiated different pressure will give you that array. And that works well from a phase diagram perspective. But the issue is the reactions we see in the element maps and in the petrography are essentially ones where, this is the detail, but really the key is that on the left-hand side of the reaction, you have olivine. On the right-hand side, you have pyroxene, clinopyroxene. You have melt and plagioclase at either side. So they are present really on, before and after. They just change in composition. But the key, really, the difference is olivine out, pyroxene in. And you can model that, and I've superimposed the model trends that result from that kind of reaction here. And this 2 times, 4 times, and 6 times trends are for different proportions of assimilation or reaction with plagioclase versus olivine. And at the time, this dates back to my postdoc in Woods Hole, we didn't really know what this ratio was. The experiments I just showed you earlier have actually now constrained that to be between sort of 1 and 2. It's not as high as we anticipated maybe when we did this study. But what that shows is you can be on a low pressure liquid line of descent. You can react with a gabbroic framework, which is what we see in the samples, and that will take your melt composition in this direction, orthogonal essentially to what used to be the pressure trend, and explaining this whole array of different compositions. So you can take your starting composition anywhere along this low pressure liquid line of descent and move it to essentially a ghost high pressure signature, which really is a signature of reaction. And if that is the case, then what we think we know about the compositional, well, the meaning of compositions rather changes. So that's important to keep in mind. And similarly, we have to worry about incompatible trace elements as well. Here's an example of a large individual clinopyroxene crystal, which was large enough to do a really detailed laser ablation trace element traverse from core to rim. And you can see here is the data. So compatible elements, of course, go down as you go to the rim because the crystal gets more evolved. As you can see, goes from green, magnesium rich to red, iron rich at the rim. So you can see a differentiation essentially on the crystal scale. That differentiation leads to an increase in incompatible elements here at the rare earths and zirconium. And titanium goes up initially, and then oxide saturate at the gray line, and then it goes down a bit. Chrome, of course, always goes down because it's compatible. But what is remarkable here is the offset between, in this case, and I've highlighted cerium versus yttrium. These are both incompatible, and the incompatibility is not quite the same, but it's close enough that it is really hard by fractional crystallization to get any differentiation between cerium and yttrium. So if you look at the cerium-yttrium ratio here in the bottom diagram, you can see that it changes by a factor of 4 from core to rim, and that's really unusual, and that is not possible by fractional crystallization, which I've modeled here. You can this is essentially, so F equals 0.21 means that there's 19% melt left at this point, which is taken actually from the major elements estimates of degree of differentiation for this crystal. But as you can see, there's no way you can fractionate to anywhere near 4. Even if you go to 99.9% crystallization, you're never going to get there. So fractional crystallization can't account for the trace elements we see on the grain scale. Now, recently there was a study that scaled that approach up from the grain scale to the scale of an individual oceanic pluton. And this is in a different place in a slow spreading ridge. There's this drill hole from ODP in the Indian Ocean, and it's got 5 plutons in it, essentially 5 differentiation sequences. This study picked apart one of those plutons, this one here from sort of 300 to 500 meters below the seafloor, which is a really nice tight differentiation trend. And they looked at the differentiation of the trace elements through that reservoir. And this is Lanthanum Sumerium. So we looked at cerium yttrium before. Lanthanum Sumerium is essentially a similar thing. You've got a slightly more incompatible element over a slightly less incompatible element. Fractional crystallization, here are the black trends, and you can pick your starting composition wherever you like, but the trend for fractional crystallization is always going to be very flat. Whereas in fact, the data on the scale of the entire pluton define this quite steep array, showing the same kind of decoupling on the pluton scale as we saw on the grain scale before. So now we can upscale this to the whole of Hess Deep. So we're back in Hess Deep where we were, and the Oman ophiolite as well. The data set as a whole, this is again cerium yttrium, so cerium here on the x-axis, yttrium on the y-axis. The data set as a whole is clearly offset towards enriched cerium compared to yttrium relative to fractional crystallization, which is this arrow here on the diagram. So our data set is offset to the right, which means you're over-enriching the more incompatible element like we saw on the grain scale and like we saw on the pluton scale. That trend holds on the stratigraphic scale. There's a lot of scatter here because individual sills have obviously individual compositions, and this is cores and rims as well, and the cores really should always be in equilibrium maybe with mid-ocean rich basalt as it came from the mantle. But if you look at the different stratigraphic levels, the orange indicates the average for that level. So this is the layered gabbros, foliated gabbros, and the very textured gabbros. And there are changes with increasing cerium enrichment relative to yttrium up section. And the same is true in Oman. So that suggests that the porous flow, reactive flow that we see on the grain scale also operates on the pluton scale and also operates on the scale of the full reservoir. There's no other mechanism really to decouple the trace elements otherwise. Now that's really interesting because there was a paper by O'Neill and Jenner in 2012 about mid-ocean ridge basalts and the trace element distributions in them. And they found that the same enrichment that we described in the gabbro, so enrichment of incompatible relative to slightly less incompatible elements, is present in the basalt as well, and that fractional crystallization can't account for those. And in fact, the correlation between what we see in the lower crust and what they see in mid-ocean ridge basalt is shown here in this diagram, and that correlation is extremely good. So what we see on that, this is back to that individual pyroxene grain. That pyroxene grain incompatible element trend compared to the enrichment in all of mid-ocean ridge basalt is very good, which suggests the same process is responsible. And if that is the case, then mid-ocean ridge basalts essentially sample part of that reactive flow in their geochemistry. So the implication for our reservoir model is essentially that porous flow happens on the full scale of the lower crust, and therefore that it is entirely, or at least largely entirely, mushy at any point in time. So we're not looking at a system where you have individual pulses of melt within an otherwise solid country rock. The only way we can explain the differentiation trend overall, plus the change in incompatible element ratios going up section, is if there is essentially porous flow on the scale of the full reservoir, which requires that it is essentially largely mushy. So we've now filled in the entire reservoir, and we can kind of summarize what we found. So it's quite vertically extensive at any point in time, and it's dominated by crystal-rich mush, but it has individual bodies that are melt-rich within it. So it's essentially a hybrid low melt fraction, high melt fraction system. Melt delivery is essentially in the deep part of the system, likely in kind of sill complexes. And then we have two modes of melt transport. We've got porous flow and episodic focus flow in sort of dike-like channels. And finally, the compositional trends that we see developing in these reservoirs are distinct from fractional crystallization and essentially a result of reactive porous flow. So these are kind of the processes that we think operate in these oceanic reservoirs. Now, the final thing I want to leave you with, mindful of the time, is a few things about, a few ideas about, where we need to go next. And, one of the things we really have to worry about is porous flow as a process and as a physical process. What are the rates and length scales on which we can do this? And what is realistic, what isn't realistic? And does that tie in with what we know about timescales of these systems? What are the mechanisms of crystal melt segregation? If we have a mush, how do you extract melt from it? Which ties in to really the physics of mush. Petrologists such as me, we tend to operate on the chemistry side of it, but we need a physical side as well. We need to worry about temporal evolution. Clearly, this isn't static, and this cartoon is obviously therefore quite simplistic and probably overly so. What is the role of melt supply? What happens if the supply is lower? Would it change the architecture? And we really overall, I think, need to go from qualitative models, such as the cartoon I've just shown you, to more quantitative models. And I'm sure there are more things that we need to worry about, but these are just a few thoughts that I jotted down. So I'll leave you with that, and then I'll be happy to take any questions.
That was really fantastic. Thanks very much, Johan. Really, really enjoyed it. A silent round of applause in the background. Okay, so I'd like to open the floor for any questions. Is there anybody that would like to ask questions to get us started?
I have a question from YouTube.
Okay, go for it, Caitlin.
It's from Samuel. It says, in light of these observations, what do you think the so-called reaction zone materializing the interaction between downwelling hydrothermal fluids and a crystal mush would look like?
We actually have some observations on that, which is interesting. We've drilled it in fact, the IDP expedition I was on, where we didn't really make much headway, drilled the expedition before in the same hole, drilled that interface. And what strikes me about it is what is in what we now see as the meltlands are these evolved, sort of very textured gabbros, and that hole also has very evolved gabbros in it. What is interesting is the interface is really quite sharp. And if I think of the geothermal gradient across it, it is quite staggering. We know that the deepest, from hydrothermal studies, the deepest temperatures of the sheeted dikes here are probably in the order of, in terms of the hydrothermal alteration, in the order of maybe 500-600 degrees or so, whereas the meltlands itself will be many, many hundreds of degrees higher. So there's a very sharp geothermal gradient corrosive, which will drive the hydrothermal system. And what we see in that hole is that the base of the sheeted dikes actually gets transformed into hornfels by what is essentially contact metamorphism. So the continued exposure to the heat of the axial meltlands below has led to extensive recrystallization of the base of the dikes to very fine-grained hornfels, which is why we couldn't drill it. The hornfels was harder than the drill, essentially, which destroyed the drill. So it's interesting, though, to see, because we know that from that one drill hole we have in the Pacific. We also have seen a few places of these hornfelized dikes, if that's a word. The hornfels is at the bottom of the dikes in Oman. But there are also places in Oman where you don't see those. So I'm not sure exactly yet what that means, but certainly the system seems to behave in different ways along axis. Maybe it relates to locations of melt delivery versus not so much melt delivery. Not sure.
That's really great. Thanks, Johan. So Jan, you have a question?
Hello. Great talk. Really enjoyed it. One comment and one question I have for you. The comment is, you mentioned that most of your work is on the chemistry of the systems, and more work on the physics would be welcome in certain aspect. It's a comment I've heard from quite a few people, and I just wanted to raise the point that, for example, on a lot of work we did ourselves, we using experiments on the rheology of crystal-rich lava. It tends to be written for volcanic eruption more than mush, but the findings really apply. And one thing that is worth considering is that when you have a lot of crystals, such as in mush, the impact of the rheology of the interstitial liquid, we find, at least experimentally, that it's reduced by 50%. So if you were to consider usually like the viscosity of a liquid, and rule of thumb, usually if you change the temperature by 50 degrees, you change the viscosity by an order of magnitude. Once you have a ton of crystals in a system, you reduce that effect by 50% roughly. So just something to think about. But certainly if you look at the Lanthanum literature that we worked on the rheology, we try to allude to mush when possible, but certainly a lot of the information is applicable. My question to you is regarding the experiments you've done, and I know you mentioned those in passing. I was quite curious about those little plagioclase blobs inside of the olivine, and it got me thinking of an older paper by Luigi Bellini and others in 2007, published in Geology, where they sandwiched some olivine aggregates with it was a basaltic glass, heated it up in a Patterson press, so temperature and pressure, and they did this to look at acoustic emission of how there could be cracking in vents, and the liquids could redistribute within the mush. So in many ways, they have some similarities with the texture you've developed, and I'm looking at some of the SEM here. I don't think that they saw any recrystallization of mineral plagioclase inside of olivines. The olivines, if anything, they have a few cracks and pores, but that's about it. Anyway, it might be something to look at. 2007 geology paper.
Yeah, sure. And back to your earlier comment in terms of the physics, perhaps I can also, or at least, if not rephrase, then add to what I said, and that we need to be better as a community. Not only do we need the physics, but also as a community, I think we need to be better at integrating the physics and the chemistry. And we need to talk to each other more. I do find, which is kind of holding us back, that, you know, chemical petrologists, if you will, enjoy talking to other chemical petrologists.
Yeah, definitely.
Physical modelists enjoy talking to other physical modelists. And we need to be much better at talking to each other.
We all need more time to do it, right? Time is usually the issue that comes in the way. It's easier to talk to the people that look at the same problem as we do.
Well, this is why we have these online seminars, so we can bring people together, hopefully. And actually, we have another question from YouTube for you, Johan, which is from Emma Watts. Hi, Emma. So she asks, can you see any evidence of the magma depth and or the plumbing system structure changing through the evolution of the Mid-Atlantic Ridge?
Yeah, this is a very interesting question, and one that we have grappled with as a community for quite some time. I mean, the old-fashioned idea, of course, was that all oceanic crust is six kilometers thick, and therefore, you know, your plumbing system ends at 6 kilometers depth. I guess since the 90s, we've probably known that the slow spreading systems have a lower heat budget because there's not as much mantle melting, so the lithosphere is thicker, therefore the plumbing system probably extends deeper. And people used to use the major elements of the basalt as their barometer. Of course, you know, I just argued that maybe that's not reliable if you have any sort of reactive flow. That hasn't stopped people from using it, by the way. So that has been our sort of our tool, and that suggested that at the Atlantic, you know, so the Pacific, you're pretty well tied to your 6 kilometers of crust because it's hot enough that you don't crystallize in the mantle lithosphere. But in the Atlantic, you start doing that, and you maybe go down a little bit further. What's really interesting now, though, is emerging work from the Arctic mid-ocean ridge, the Gackle Ridge, which is the northern extension of the Mid-Atlantic Ridge, which goes all the way towards Siberia. We now have melt inclusion evidence since 2 years ago of crystallization down to 16 kilometers, which is rather a lot deeper than I think anyone had considered reasonable. And micro earthquake evidence from the same place, from the Gackle Ridge, now suggests that the mantle lithosphere might be up to 30 kilometers thick, in which case, you know, it's possible that crystallization goes even deeper. So certainly there is an effective spreading rate here. This, you know, what the reservoir model I've just developed is clearly a fast spreading one. If you go to the slower end of the spectrum, it will be more intermittent, probably not as continuous, and extending over a greater range of depths.
That's really interesting. I'm going to, if I can, take chair's privilege and just ask the last question because I think we're running out of time. And I guess it's, I'm more on the sort of physical side, so it's a bit of a question about some of the physical implications for what you've been suggesting. And I guess I was particularly intrigued by the sort of aligned flow features that you're seeing in the gabbros, and you have this sort of model of diking basically coming through and dragging those crystals up with them. And so I guess that means that there must be periodic times where there's quite high strain rates basically, so you can kind of like crack your way through the mush, and then actually the evidence for it might be erased other than potentially that kind of alignment that you're seeing. But I did wonder about that process of aligning actually might if you think about it like step by step, it kind of creates like a preferred pathway for the magma. And so I did wonder about, because the patterns seem to be quite distributed and homogeneous in their alignment rather than focused. And so I wondered about what your thoughts on that were, and also about like the role of degassing. And so maybe like gases moving through the system might be responsible for aligning things rather than melt. So I just wondered about what the chemical side says about those kind of things.
Yeah, I guess from the gas perspective, our current understanding is that the volatile contents in mid-ocean ridge basalts are not high enough to lead to volatile saturation in the reservoir. Because also we're under, 3 kilometers of water, so the pressure is a bit higher anyway. And so degassing is probably unlikely, at least in the case, interesting though, in Hess Deep, because it's a mid-ocean ridge with a true mid-ocean ridge basalt chemistry. Oman ophiolite, of course, is slightly wetter because it formed in a subduction environment. I don't think anyone has argued that there has been volatile saturation in Oman, but then I don't think anyone has actually looked at it. So there is, I guess, that would be something that's worth exploring. In terms of the focusing, I can't say that we have any sense of whether that happens or not, because all we've got is a few spot samples up the slope. So we lack a sort of a field context that you would normally have. The field context, of course, we have in Oman, and that's where at that level, what you tend to see, but again, it's understudied, no one has really focused on it, and what it would actually make a really nice study, is we seem to see, if you go to an outcrop of that foliated gabbro level, you seem to see channels of different compositions, sort of on a 10 centimeter scale or so. So you might see an olivine-rich gabbro and then a gabbro, an oxide gabbro, different compositions in a sort of vertical channel-like fashion.
Yeah.
It would be really interesting to see, from a chemical perspective, what kind of different melts you see transported, but also B, from a physical point of view, what the fabric evolution looks like, between the different channels, where they all have a fabric, where they have the same kind of fabric, where the intensity changes. That would essentially answer your question, to which I now don't really have an answer, but it's certainly something that's worth someone doing.
Yeah, that sounds really interesting, and yeah, lots of new work to do, and hopefully new collaborations bringing together the physical and the chemical, which is really cool. So,
yeah.
Okay, so I think we'll have to draw the question and answer session to an end, and thank you again, Johan, for your fantastic seminar.
Thank you.
For those of us who are on the Zoom, we can also go now to Gathertown, because Johan's going to be available for a bit to have a chat there if anybody would like to continue discussions. So thanks again, Johan, it's great to see you, and thanks to our viewers on YouTube.